great. Can you all see my screen? Perfect. Okay, so let's see if I can put this on, minimize it somehow. Okay, perfect. So hi everyone. Today I'm going to be talking about a bidirectional approach that we have constructed to compare specifically the modular structure of networks. And so yes, this is work that I've done in conjunction with Daniel Strelino and Neve O'Clery, who all of us were in the Maths Institute, and now Daniel and Neve have moved over to UCL, specifically at CASA. So sort of to start, the motivation for this project was a specific problem in the economic geography field. And that is the problem of comparing the different countries' skill-relatedness networks. Just to check, has my slides moved over? Because I know often this is a problem. Okay.
Yes, they have.
Great. Okay, so the skill-relatedness network is a network that's normally constructed for a country or an economy. The network you can see here is specifically the network for Ireland. And the network consists of nodes, which represent industries within an economy, measured according or defined according to an industrial classification scheme. And then the edges in this network is a measure of the skill relatedness between two industries. So this is a measure of the skill similarity between two industries. So the amount of skill overlap or knowledge overlap. And it is quantified by comparing the number of job switches between these two industries and compared to what is expected at random. So for example, comparing it to a configuration model. Now, these networks are used within the field specifically to model regional growth paths and to construct industrial diversification strategies. So how this is typically done is the network is constructed for a country, and then a region within this country's industrial portfolio is projected onto this network. And then according to where the nodes, which are these industries within the portfolio, lie within the network, either in the center or in the core of the network or more in its periphery, it determines what industries it can move into or diversify into. And this is typically modeled using a branching process on this network. Now, a recent paper by Neve O'Clery and various co-authors sort of showed that a key aspect of these networks is their modular structure. So the communities within this network can be seen or represent skill basins. In a sense, so this is a group of industries where workers are able to freely flow between these industries, and there's a high degree of sort of knowledge and skill overlap. But what is really key about this community structure is that it also constrains sort of knowledge diffusion on this network and industrial diversification opportunities. And this is exactly what these networks are used for in the field. So when comparing these networks across countries, it's key to look at the modular structure of these networks. Now, in these networks or in various other applications of networks as well, it is often so that you don't only look at a single partition of the network, but look at sort of a range of partitions at different scales. So you can think of this as using a community detection algorithm with a resolution parameter. So considering the modular structure where maybe you have many smaller communities up to where you have only a few but large communities. When considering these partitions sort of in relation to each other, you can further learn about the structure and the modular structure of the network and how these sort of partitions fit together. So if we look here, this is specifically a dendrogram that comes from this paper that looks at the modular structure of specifically the Irish network. But here on your x-axis, you have the various resolutions at which different partitions are found. And then on your y-axis, you have maybe at a very small resolution where you have many smaller communities, you just have the names of these communities. So this gives us more information about how this modular structure fits together. So how it either merges or joins together, and gives information about how knowledge and skills fit together and flow within an economy. Okay, so just going back to sort of the motivation of our modular comparison framework is that we want to compare these networks across different countries. Now, the reason why this is quite interesting for us is that commonalities in the structure could show us that how sort of economies are fit together in terms of skill is universal. But also, if there are differences between the modular structure, this can unveil potential new growth paths and opportunities. So by this, we mean one country can potentially learn from the modular structure of another country and see hidden links or ways in which it can improve its industrial diversification. Okay, so this has now been a very specific problem that motivated our framework, but just to sort of show that there are various other applications in which the modular comparison of networks is of interest, is here we look at a paper that came out quite a while ago that also did this. It took two networks, or maybe quite a few networks, and did the pairwise comparison of these networks, focusing on the community structure. And these networks were neural networks, where each node within the network shows a region in the brain, and each edge shows functional relations between these regions. And then the modular structure of these networks were calculated, and they were compared between sort of a set of networks which included brains of healthy participants and a set of networks where patients had schizophrenia. So this is just another example of where it could be applicable. Okay, so if we now look at exactly what is our, or sort of to characterize our problem, we want to compare two networks, G1 and G2. And in our problem, we are going to say that these two networks are node aligned. So they actually have the same node set and only a different edge set. And we're also going to say that each node within the network has a specific label or identity. So the node is a specific industry or a specific region in the brain. And then we want to compare the modular structure of the networks. So we are going to be given two partitions of these two networks that describe its modular structure. So P1 and P2, which is defined on this vertex set for both networks. Okay, so also at any time, please stop me if you have any questions or for clarification. But if we now look at just in general, the literature out there of comparing different networks, there are a broad range of comparison techniques. And here we've sort of only highlighted a few of them, and we've arranged them on a scale according to what specific feature of the network they consider within the comparison. So this feature can go from, if we look at the red region on the left, it's really a micro scale, where you consider only local properties, maybe of each node within the network, and you compare them across two different networks, all the way to a macro scale, where you're comparing some global feature of the network. And we are specifically interested in this mesoscale, this intermediate scale, in which we've placed sort of the modular comparison of networks. Now I'm going to highlight sort of three comparisons and or network comparison techniques and show some of the limitations using a toy example. But so I want to focus first, if you look at the micro scale, we have the region there called structural distance. And this specifically, the Hamming distance, is quite a well-known distance that's used broadly. And what this distance is, in a sense, is it really calculates the similarity between two networks by saying how many edge deletions or insertions do I need to do to transform one network to another. Okay, so you can easily argue that this is, in a sense, quite a basic measure, could be good for its simplicity. But as many people have pointed out, this measure is highly dependent on the density of the graph. And because of this problem of graph density, the Jacquard distance was introduced. And this distance is exactly the same in a sense as the Hamming distance, but it just normalizes for the density of both groups. Now, what I want to point out about microdistances, and specifically this Jacquard or structural distances, is that they are very local, so they only look at the direct neighborhood of each node. But also, every edge insertion or deletion or difference between the two graphs is treated equally. So if you add an edge between two really important nodes in your network, or an edge that joins two communities in a sense, it is treated exactly the same as an edge maybe right on the periphery of your network. So this is a limitation of the structural distance, also in sort of relation to our approach. We then jump to right to the other side of the scale, and we look at sort of a macro distance, specifically looking at a spectral distance. We want to highlight sort of eigenvalue comparison, which is also a quite well-known and well-used technique. And in eigenvalue comparison, the eigenvalues of a network, specifically of either its adjacency matrix, but maybe more commonly its combinatorial Laplacian, is calculated and compared across two networks. Now, this is basically, you just take the difference between either the whole range of eigenvalues or maybe sort of a weighted function of them, maybe focusing only on one or two of them. But as the eigenvalues tell us about some topological information about the graph, specifically maybe its connectivity, and this measure picks up the difference between the connectivity of two graphs. Now, the limitation in the spectral distance that I want to point out is that because of these eigenvalues, each node doesn't actually have a label. So the measure is permutation invariant. Okay, but now I want to focus now, if we look at the middle of the scale, on modular comparison, which is exactly what we are really interested in. And a very well-known technique here that's used widely is the NMI, or the normalized mutual information. Now, many of you might be quite familiar with this technique. It is borrowed from the field of information theory, and it calculates or defines the similarity between two partitions as the mutual information of the two partitions normalized by a combination of each partition's entropy. So NMI, in a sense, measures how easily one can infer one partition given the other. Now, there's also various limitations and various other measures, such as RMI, which is the reduced mutual information, has been brought out to look at some of its limitations, specifically that if the two partitions have very different or starkly different number of communities, NMI doesn't do so well. But now what I want to specifically point out about NMI is it only considers the partition on the graph, and it doesn't consider any of the underlying topology of the network. Okay, so to further sort of show these limitations, we're going to look at 5 specific toy examples and see how these 3 measures that I pointed out perform when comparing these toy networks. Okay, so here we have a network, if you look at network A, and we're going to compare it to network B, C, D, and E. So I want to point out, if you look at network B and network C, these 2 graphs are similar in a sense to network A, but in each one, either node 6 in B and then node 1 in C have been moved to the yellow community. Then network D is a network that seems to not really have modular structure. And then network E is specifically a nested version of network A. So it seems like the blue community has been split into 2 smaller communities, where the blue community, I'm talking about the blue community in A, in E. Okay, so we're going to compare A to each of these networks. So if we now look and see how these 3 distances do, the Jacquard distance, which is the local distance, spectral, which specifically looks at this connectivity or the comparison of the eigenvalues, and then NMI, which really compares the partitions. So first we can see in the Jacquard, we see Jacquard ranks network B to be the closest to network A. So AB means the comparison of network A and B. Then the spectral distance says A and C are the closest together. So in a sense, these have the most similar connectivity. But then specifically, if we look at NMI, we see that A and E are the closest together. So this measure is picking up that network E, in a sense, is the nested version of A, or that A's blue community is broken up into two. And you can argue that these two are very similar. But what we want to specifically point out is that NMI rates the comparison of A and B and A and C to be exactly the same. So the exact same distance is obtained. And this makes sense because NMI only looks at the partition. So in each of these graphs, just one node is placed into the yellow community. But if we look at the actual node that is moved, so this is either node 1 in C or 6 in B, we can argue that these two nodes are slightly different in the community structure of A. So looking at network A and specifically looking at the blue community, we can see that node 6 is quite connected within that community. It connects to all of the nodes except for node 1. But on the other hand, node 1 is only connected to 2 of the nodes. So it's, in a sense, more on the periphery of that community. So we could say if you move node 1 into another community, which C does, this could be actually more similar to network A than moving a very central node, such as node 6 in the example of B. So we want to point out, specifically in terms of NMI, two problems with NMI in a sense. The first is that it doesn't consider the underlying topology of the network or the quality of the communities when it compares two different networks. Now, the second limitation that I want to point out is not as clearly or not really shown here in this example, but that the measures don't consider how a community is defined. So by this, I mean, if you apply a community detection algorithm to a network, you're going to consider how that network is constructed or its application. So you're going to consider maybe if there's flows in the network, you're going to think of what a community means in order to maybe conserve that flow. So you're going to use a dynamic community detection algorithm. Or if there aren't really flows on the network, maybe in a friendship network, you'd rather use a structural community detection algorithm. Now, this idea of considering exactly how a community is defined and that it's defined slightly differently with different community detection algorithms isn't taken further into the comparison of two networks. So these are the two limitations that we are going to try and solve with our new approach for the comparison of modular networks. Okay, so we are going to define our bidirectional distance. And just before defining it, we first want to define the quality function f, which is a quality function that measures the goodness of fit of a partition according to some desired property. So f could be, for example, modularity or stability or a specific quality function. And in this quality function, you are considering exactly how a community is defined, in a sense, and how well it's normally used to sort of find a community structure on a network and define how well the partition describes the modular structure of the network. So we want to compare the modular structure of two networks, A and B. And as we said, we are given their two partitions. And in our distance, we're going to assume that these two partitions that are given to us, in a sense, maximize the quality function, or it's a near optimal partition that is found by maximizing the quality function using some heuristic. Okay, so our distance is quite simplistic, and in a sense that we think this is a great advantage of it. And it consists of two parts. So the first part, or score, which we're going to say is the distance of AB, is equal to 1 minus a ratio. Now this ratio is the quality function when you take network A and you project network B's partition onto network A, and you determine the quality of that partition. And then you divide this by the quality obtained when taking network A again and using its own optimal partition. So what this ratio, in a sense, is telling us, so we go 1 minus the ratio just to make it a distance measure, but it's how well network A describes the modular structure of network B. So we know that we can't take the quality function and compare it across two different networks, but note here that network A is consistently used. So it's the partition of B onto A, projected onto A, over the quality function obtained when taking network A and its true modular structure. And now by construction, this score, this distance, lies between 0 and 1. But now we do this in reverse. So we take the second network, network B, and we calculate the same thing. So we go 1 minus the ratio of network B, where the partition of network A is projected onto network B, divided by network B when using its own optimal partition. So the second part now tells us how well does network B describe the modular structure of network A.
Can I ask a question, Mattie?
Yeah, go for it.
So by construction, this will lie between 0 and 1, only if you found the global maximum, right?
Yeah.
And,
so
typically with heuristics, you only get a local maximum. So did you ever see, I mean, I don't think that it will happen very often, but did you ever see that actually B was a better fit than A?
Yeah, so that could happen every now and then. In that case, we would say, well, then B's partition would be a better fit for A. So then we use that as an optimal partition.
Mm-hmm. Yes, I guess you simply switch it.
You simply, not switch it, but you'd make both of them's partitions then be the same.
Yeah.
Because the one would better describe it.
Yes.
Yeah.
Thank you.
But yeah, cool. So then sort of just to define our whole measure, why we call it the bi-directional distance, is we take these two scores and then just put them together. And these two values together, sort of in a XY plane, would give you our bi-directional distance. Okay, so we have three main advantages of this distance, which I'm going to run through and then give various examples and toy models to really show you these advantages. So the first is the measure considers the underlying network structure. And this is, it has a quality function, it's considering the edge values, and it's considering the strength of connections within and between communities. Then secondly, it considers different community detection algorithms. So this is where you're saying it considers how you would potentially define a community in the network. But we realize that this is only true if the community detection algorithm is based on optimizing a quality function, because our framework uses a quality function in a sense. And then the last advantage is that it's able to identify cases in which dissimilar partitions hide that the community structure of two networks are relatively similar. So to maybe explain this a bit further, is if you think about, if you have two networks that are very, very similar, and you use modularity to find the community structure on these two networks, we know that modularity has a really flat landscape, and you could obtain two partitions that are both sort of close to optimal or in local maximas, but could actually be quite different. And in this case, as you project these community structures across, if these networks are really similar, our measure will be able to pick it up and give you a distance close to 0, even though the partitions found might be seen as quite different. Okay, so now if we look, how does our measure perform? If we just go back to the first 5 examples or toy models we considered using the limitations of some of the other network comparison techniques. So the first thing to note here is we have 2 dimensions to our distance. So we've projected this onto an XY plane. And what is really interesting about the measure is specifically when we get a distance measure that's asymmetrical in a sense, or that lies far from the y is equal to x line. So when we specifically look at the pairwise comparison of network A and network E, so if you can see, it's a dot that looks like it's lying on the y-axis. It's 0 in terms of its distance in the x dimension, but in the y dimension, it has a distance slightly larger than 0.2. Now, this is really interesting because it shows us that one network is able to describe the modular structure of another network really well, but the reverse is not true. So if you can remember network A and network E we sort of argued was a nested version, or the blue community was split into two smaller communities in network E. So here we have an example where if you take network A's modular structure and you project it onto network E, you are combining these two smaller communities. So in a sense, you're getting quite a good quality function, and therefore you're getting a distance measure of 0. But if we do this in reverse, and we take the modular structure of E, and we project it onto network A, we're splitting the community, the blue community, into two communities. And therefore, we're not getting as good quality function, and therefore a larger distance. So our measure is able to pick up that there's a sense of nestedness between these two communities. And then just also want to point out the comparison of network A and B and A and C. And if you can remember, because NMI was only looking at the partition, it measured these comparisons to be exactly the same. The exact same distance was obtained for the pairwise comparison of A and B and A and C. But if we look at where A and B and A and C lie in our scatter plot, we have that the distance between A and C is smaller than A and B. And as we argued, if we looked at network C, the node that's moved into the yellow community lies more in the periphery of the modular, or of the community in network A. So we could argue that these two networks are more similar. Then just also, D doesn't really have a modular structure, so we can very easily see that A and D lies quite far. It has a high distance in both dimensions. Okay, so we're now going to see, or sort of show, how our measure performs when we consider the comparison of two networks that have different sort of network characteristics. So the first thing we want to look at is what happens when we compare two networks where the community structure is defined in different strengths. So by this we mean we reduce how well the community structure is defined. So we create a family of stochastic block models where in each one we implant a specific modular structure. And this is 4 equally sized communities, as you can see very clearly in network A1. Then in each consecutive network, we reduce the intra-community strength. So there's less, in a sense, there's less edges between the nodes within the community, and the community is less well-defined. So we compare network A1 to A2, A3, A4, and A5, where A5 seems to not really have modular structure at all. The inner and the outer probability of edges are actually the same. So it's really just a random graph. So if we look at how our distance measure performs, if we look at the scatter plot, we can see when we compare network A1 to A2, A3, and A4, as the modular structure is less well defined, our measure increases in one dimension. So this is really the asymmetric behavior that we are seeing. So what this means is that one network is able to well describe the modular structure of each of the other, but the reverse is not true. So sort of to further explain this, network A1's modular structure can well define the modular structure of A2 and A3 and A4. And this is because this is actually the true modular structure that we'll be projecting onto each of these networks. And that's why we get a close to 0 distance value on your Y dimension. But when you project the not so well-defined communities onto network A1, you're splitting up a community that is very well-defined. And therefore you get increasing larger values on your X dimension. And then when you compare A1 and A5, where A5 doesn't really have a modular structure, we see that our distance measure sort of increases or jumps where it's large in both directions. Okay, so the second sort of network characteristics we want to consider is when you compare two networks where one is a nested version of the other. So by nested here, we mean you take a community and you divide it into smaller communities. So a refined community. So to show this, we again construct a family of stochastic block models. If you look at B1, we implant a specific community structure of two equally sized communities. And then in each consecutive network, we take the largest community and we split it into two communities. So you can easily see that happens for network B2 as well as for network B3. Then for network B4, we take the largest community, or as they're all equally sized, one of them, and we just divide it into three communities. Instead of doing this consistently over and over and over again, we just show B5 and where all of them have been divided into three communities. So now we compare each of these, which is we argue to be slightly more nested or refined, to network B1. So if we again see how our measure performs, if we look at the scatter plot, we can see for each consecutive network, our distance again only increases in one dimension. So our network measure again is able to pick up that one network better describes the modular structure of the other than vice versa. So when we take network B1 and we take its modular structure and we project it onto B2 or B3 or B4, we are combining smaller communities together, and therefore we get a really good quality function. So we get a distance value of close to 0. But when we take the modular structure of B2 or B3, where they are in a sense smaller communities, and we project it onto B1, we're dividing a very big, well-defined community into smaller communities, and therefore we get a weaker quality function value and a larger distance. So we want to show here that our measure is able to pick up this behavior by only increasing in one dimension. Okay, so the last sort of network characteristics that we want to point out, and this is specifically just to show how our measure picks up the underlying topology of the network, is again, we have three stochastic block models. And the first stochastic block model, we've divided into three equally sized communities, as you can see in C1. Then in network C2 and C3, we divide both of these networks into four equally sized communities. And this is, in both of these networks, the strongest community structure, and in a sense would be picked up by a quality function as sort of your global partition. But in C3, we see that two of these communities have a higher sort of inter-community edges. So 2 and 3 are more closely connected to each other in network C3. Now, what is interesting here is that if you take network C2 and C3 and you compare them to each other, you get a distance value of 0, because these partitions are exactly the same. But if we compare another network, so C1, to network C2 and C3, we can see that we obtain two different measures. We want to point out here that although the community structure of these two networks are shown to be the same, our measure is able to pick up that the underlying topology of these two networks are different and will obtain different distances. Okay, great. So now we want to also show you just how our measure performs when we don't use, or when we use different optimization functions. For all the previous results, we've just used modularity for simplicity. But here we want to show how does our distance value differ when we use modularity, and we're also going to use now stability and infomap. So to show, we're going to take network A, which is just a ring of rings, and it actually comes from this paper by this Markov dynamics, the one that's referenced at the bottom. And we're going to compare this ring of rings to a ring of cliques, or circular graphs, sorry, with connecting set 1, 2. So if we take three different optimization functions, specifically modularity, stability, and infomap, and using their community detection algorithms, we find the modular structure of each of these networks. And if we look here, first looking at network A, which is just a ring of rings, we can see that each of these community detection algorithms are slightly different communities. So as many of you probably know, infomap and modularity seem to over-partition the network. So this is a well-known problem with these two measures, specifically called the field of view limit. And instead of placing each ring into its own community, it takes a certain segment of the ring and makes it its own community. While stability, as it looks at sort of many steps in the dynamics, it can consider each ring as its own community. Now, if we take the graph, the ring of circulant graphs, we can see that by enhancing the click-like structure of the communities, each of these quality functions or community detection algorithms can correctly classify the communities. So this is because the field of view limit sort of tells us that infomap and modularity underlyingly define a community to have a click-like structure. And that is why these two community detection algorithms over-partition the network. So if we now just see how our distance measure performs when we use these different measures, we can see that we get a different distance. We get a different distance for stability, and infomap. So what we really want to point out here is that in a way this is a limitation to our distance, but our measure is only as good as the partition that is found. So if the underlying community detection algorithm that is used has some limitations, it's going to be brought over into our distance measure. But this is true of other network comparison techniques as well, such as NMI. Now, we also want to just point out that this also shows us that we can't compare a distance value found using stability, maybe on two networks, to the comparison of another two networks using a different quality function. So in order to make these distance values comparable, we're going to have to use the same quality function, or at least take or understand why these might be potentially different. Okay, so we just also want to show you the amount of additional information you can gain when you use a multi-resolution optimization function, and sort of how our technique can do, or our measure can do, from a multi-resolution perspective. So just to show you this, we are going to compare three networks. Now, so we're going to look specifically at nested networks, where two of the networks are similar in one sort of range or scale. So just if we focus on network A, we can see it's a nested network where at a high level, it is broken down into three equally sized communities. Each of these communities are then divided into two communities and then once again into two communities. So at a very fine scale, it is broken up into 12 equally sized communities. Now, if we look at network B, it has a similar high scale community structure as network A. So it's also divided into three equally sized communities. But then how these are further broken down is different. So it's broken down into then three communities and each of these into two, but not equally sized. If we look at network C, we want to point out that at a fine scale, network C consists of 12 equally sized communities, which is exactly the same as network A, but then how these are aggregated are very different. So we really just want to point out that network A and B are similar at a high scale. So when you have three equally sized communities, and A and C are similar at a very fine scale. So they both have 12 equally sized communities when you're considering the fine community structure. Okay, so if we then see how our distance measure performs when we compare A and B and A and C. So we want to point out here you have two heat maps because we have two dimensions to our distance. We can, if we look at A and B, on your x-axis, you have resolution parameter alpha. So this is the resolution parameter used, and then also the different partition that is obtained for graph A using this resolution parameter. And then on your y dimension, you have resolution parameter beta, which is the different partitions you obtained of network B when using beta within your quality function. And here specifically, we've used stability as our quality function. So if we look at the two heat maps of A and B, and yellow regions tell us where the distances are very small, we can see that at a large resolution parameter of both alpha and beta, so where network A and network B's community structure is defined with large communities, they are very, very similar. So we can remember that these are the two networks where they both have 3 equally sized communities. But then as you reduce the resolution parameter, in a sense are reducing the size of the communities, they become less similar and then slightly more similar when it's at a very fine scale. If we then look at the comparison of network A and C at a very fine scale, so when you have 12 equally sized communities on both of these networks, we see that the distance is very small. And then as the community structure of these networks increases and larger communities are defined, we see that our distance measure increases. So with this example, we just want to point out the additional information that you can gain when comparing two networks when you look at the full range of partitions of both of these networks. Okay, and then basically to conclude, we want to go back to the initial motivation for this paper, which was to compare the skill-relatedness networks across different countries. So here we have the comparison of Ireland's skill-relatedness network with that of Germany, the Netherlands, and Sweden. So if we see how our distance measure performs, if we look here at the scatter plot, we can see that the comparison of Germany, the Netherlands, and Sweden, so the pairwise comparisons of each of these, we get a low distance. And in a sense, we can see that these modular structure of these countries are very, very similar. But then if we look at the top, we have this comparison of Ireland to each of these countries. So we can see that the Irish modular structure is quite different to that of the other 3 countries. Now, a really interesting finding here is specifically if you look at the dot of Germany, the comparison of the German skill-relatedness network and the Irish skill-relatedness network. And what's really interesting here is, again, the asymmetry that we find. And when looking at the 2 networks, we can see that the Irish skill-relatedness network has communities that are a nested or refined version of the German skill-relatedness network. So this is really a great finding for Ireland in a sense, because they can now learn from the German skill-relatedness network to see where 2 communities can potentially be joined and sort of additional industrial diversification opportunities may be available, which they can't see from their own network. Okay, so finally, just to sort of conclude, the key things we want to sort of just remind you of about our distance measure is the advantages of the distance measure is that it uses the topological information of the graph in the modular comparison. It is also able to be used with different community detection algorithms, but again, these have to be by maximizing or using a quality function. And third, it can identify where dissimilar partitions may show similar modular structure. Now, some of the limitations of our measure is that, as we've previously pointed out, our measure is only as good as the partition that is found. But we do argue in the paper that our measure is able to better handle this than other measures because it does take the topological information of the network into account. And also the distance obtained should not be compared across different community detection algorithms and using their corresponding quality functions. So this is, we can't compare the value obtained when we use modularity in our framework and then use, for example, stability. And then just finally, our measure is not a metric as it does not hold to the triangular inequality. Cool, thanks.
Thank you, Mattie.
I'm going to try get back to the meeting.
Yes. Are there any questions? Somebody might want to start. I have a couple. No?
I'm trying to like get everyone's faces again.
Yes. So you should stop sharing your screen.
Ah, okay.
So Alexandre.
Can you hear me?
Yes.
Hi.
Hi. So thank you very much. It was really nice talk. I was just wondering if it's maybe something I misunderstood or not. But so can you compare partitions using the same quality function, but using different resolutions?
Yes, so you can when you use the same quality function, them, but just not when you use different ones.
But if you change the resolution, it won't change the bounds of the quality function?
No. So I don't know if you can remember the two heat maps, but in that example, we were changing the resolution parameter. Yeah. So it was the resolution parameter within the equation was also changing when we calculated the distance, but the same quality function was used. I don't know if that's exactly what you're asking.
Yeah, I think so. That's the question. Okay, thank you.
Any other questions?
You had a question earlier about the fact that you might not have a global optimum. And so maybe the B partition might be better for A. And in that case, you could just swap it and update the partition for A. What about cases where maybe the partition you found from A is just slightly better than the B partition for graph A, but they're completely different? I guess I'm slightly worried that your partitions might be sensitive to noise in some way, and that would make it so that if the B partition that looks slightly worse given the noise is actually a better partition for what's actually going on in A. Have you thought in those directions at all?
Yeah, so that's a great question. I think as we've pointed out, a sort of problem of all actually community detection algorithms that just takes a partition is that partition has a sense of robustness, or whether it really defines the true community structure. So we are aware that, for example, in the modularity and infomap example, the partition didn't as well describe the community, and therefore we got a different distance. So our distance is sensitive to that. But we argue that because we are taking the edges into account, we do slightly better. We have proposed in sort of future work maybe to add a sort of robustness score to the measure, which could help with how well does this partition really define the community structure. But we're focusing on the network comparison and saying our partition is given to us. But it is a great problem, and I think a problem of community detection just in general.
Yeah.
I don't know if Daniel, if you want to add anything or Neve to that question. If not, yeah, but thanks. Yeah, that is a concern, or thanks for the question.
Thank you. Anything else? So I'm gonna ask mine. So mine was about, so related to this point is that, so I was surprised to see that in the many examples where you were using stochastic block models, the quality function was not the one you normally use for stochastic block models, which is the log likelihood, no? And for stochastic block models, you can put in a prior that is a regularizer for the number of communities. So whenever you start losing this community structure, then there is no evidence for communities, and then the number goes down, right? And you just put everyone in the same block. And so my question / suggestion is, what do you think would happen if that's the quality function that you use? So in a way, it does the opposite than modularity, right? When you don't have enough evidence in modularity, the number of communities grows. And this is the opposite. This would do the opposite.
Yeah, thanks. That's a really interesting question. So we haven't really investigated that as we were using sort of more the traditional quality functions. But it would be great to see how the distance sort of performs. I think it would still maybe just increase in one dimension. So it will still show us that similar behavior.
Mm-hmm.
But yeah, that's a great suggestion. I think it's a cool thing to add to the paper. Thanks.
No worries. Anything else? You didn't get any backup from Danielle.
Seems not.
If not, and yeah, I don't know. So this is a good place to stop if there are no more questions. I didn't see anything in the chat either. So let's thank Mattie once again.
Yeah,
Thank
thanks
you
so
for
much.
joining us. All right.
Cool.
All right. Thank you. See you all next week. Okay.
Cool.